Alrighty, so hello and welcome. Took like a half an hour break. I don't know, I wanted to just hang out for a minute or two. Yeah, I don't know, just kind of suddenly striking me, realizing that like all these algorithms have a have some optimal approach that you're never gonna be able to figure out unless you spent inordinate amounts of time trying to figure it out. Unless you spent a lot of time. Not that you couldn't ever figure it out, but it's very likely that yeah, hold on one second, I'm trying to set up my chat. Oh, but yeah, what you have is, you have all of these solutions are such that either you find a naive solution or sort of a regular normal solution, or you dug up some algorithm someone figured out many years ago, and usually not simple. Not something. I mean, it's not simple, but it's not something you'd ever think up on your own, really. So I don't know. Kind of just thinking about that, realizing that like you're better off really just reading like what algorithms other people have come up with already for a lot of these problems. Take a look at the discussion, find a more optimal approach. If I point you to the paper there. Yeah, it's kind of disappointing, I guess, but whatever, I guess. And it's kind of endless. It's kind of endless. Given a positive integer n, find the smallest integer which has exactly the same digits existing in the integer n and is greater in value than n. If no such positive integer exists, return -1. Let me whisper instead of speaking. Note that the returned integer should fit in 32-bit integer if there's a valid answer, but it does not fit in. If it does not fit in a 32-bit integer, return -1. Alright, so positive integer n, smallest integer is exactly the same digits existing in n and is greater in value than n. Okay, that's pretty interesting. The integer should fit in a 32-bit integer if there's a valid answer, but does not fit. Return -1. Fair enough. So I'll probably use longs to store the number, just to keep it simple. Just check if the long is a long, and just check if it's larger than the largest value of n, which would be like int max, and return -1. Otherwise return, put it back into an integer, 32-bit integer, and take that. So the smallest integer has exactly the same digits. Okay. Let me lay down for a moment, or just sit down for a moment and ponder this. So this is, I think, very similar to some other problems we worked on where... Excuse me. We're rearranging digits to get larger values. So, since all of the digits are the same, you can perform a sequence of swaps. Another way of looking at this is to take all of the permutations and take the permutation that's the smallest permutation that's larger than this value. So, I mean, you could take all the permutations, take all the digits formed by the permutations, sort them in a list, and then perform binary search over that list. Since the number's in 32 bits, I think there's only 18 digits you can have. Sorry, it's only 9 digits, I think, at most. So you can do, let's see, 2 raised to the 31st, log 10, yeah, at most, no more than 9 digits. factorial is 362,000. So we can do a pretty slow solution to this. Would be to actually break up the digits into a set of digits, and then just loop over every permutation, and generate the number from every permutation, and then take all those numbers and put them into an array, sort the array, and find the number that we're looking for. And that's fine. That would be relatively efficient. I don't know what the time bound is for this problem, but probably that would be fast enough. Also, don't forget to convert all those numbers to longs. That's one approach. Not a particularly efficient approach. It's log of n factorial, but it turns out to work out okay in this instance. I actually don't know how quickly it would be for me to code that. I could program that and try it and see if it works. Finding all of the permutations is kind of tricky though. I think it's not too bad. Just thinking. Yeah, usually I use some kind of a bit set, I guess. Yeah, that works out okay. You can use a bit set and then loop through the bit set at each iteration. That should work out fine. Excuse me. Can we use a bit set here? Let's see. Hold on. Let me check. If we can use a bit set. Not sure that we can. It's templated, but I don't know. I think that in order to use a bit set, you need to know the size. I mean, I guess we could use a bit set of size 10, something like that. But no, actually, you really need a bit set of the size that's being used. Excuse me. So we'll just use a vector of booleans then. Yeah, so we can go through all the permutations, that's fine. Before I start coding this, let me see if there's another answer we can come up with. So we can, as mentioned, you could rearrange take all the permutations, dump them into longs, the resulting integers, sort that list, dump that into a vector, sort that vector, perform an upper bound search, or excuse me, really would be a lower bound search on well, it would be an upper bound search, yeah, upper bound search on the array, and that integer there. If it fits into a 32-bit integer, if it exists, return it. If it exists and it fits in a 32-bit integer, then return it. Otherwise, return -1 if it doesn't exist, or if it doesn't fit in a 32-bit integer, then return it as a 32-bit integer. Yeah. That's it. That's a pretty simple DFS search recursion, depth first search recursion, and just push all of the final results into a return vector at the end. So, yeah. So what I'd like to do is think about a better solution than that. Because while that will work, that's not the best. That's not the best. Could probably code that up pretty quickly as well. But what I'm thinking, what I'm looking for is, what else can we do? Excuse me. Well, if you want to get a number that's larger, take any two digits that are not equal, such that a larger digit is to the right. So, if at any point you have a digit to the right that's larger than one of the digits on the left, or if there's any digit for which on the right side of that digit there is a larger digit, excuse me, yeah. Then if you swap those two, you'll end up with a digit that's larger, you'll end up with an integer that's larger than the original. So, every possible integer that's larger than the one we have consists of some series of swaps, such that at least one of those such a swap occurs. Now I think if we want to minimize our number, we have to do two things. One, we need to find a swap such that we have a larger number, but we also need to make sure that all the other digits are arranged in such a way that it's the smallest possible number. So I guess what you would do is, I'm actually not sure if there's a really efficient way to figure this out, to do this. I don't know. Maybe. Maybe not. I guess what you'd want to do is, I actually have no idea. I have no idea. Well, first thing it's not necessarily the case that you'd want to, I want to say a form of a greedy algorithm is what we want, but I don't think that works. You could do, you might say something like, well, if you find two digits such that a digit to the right is two unique digits, or two different indices, where a digit to the right is larger than the digit to the left, you could swap those digits, and then sort the remaining digits that are to the right of the swapped digit find the least significant digit for which there is a digit to the right that's larger. Interesting. Can you find that? Well, I mean, you could do that with 81 passes. I mean, that's fine. You could do that in quadratic time. But maybe you could do that in linear time. Find the digit to the right. Find a digit that has a smaller digit to the right. And find the... Well, actually, what you can do is... I guess you could create a... I guess you could do an n log n time from right to left, which is pretty good. Basically, you put each number you see from each digit from least significant to most significant. The first number obviously doesn't have a digit to the right. That doesn't have anything to the right. The first index here doesn't have a smaller digit to the right. But for each index, you can insert into a set the digits that you've seen so far. Before you process each digit, the previous digits you put into a set, and you say, find, basically, is this the largest value of that set or not? And if it's not, then you found what you're looking for. I think that's it. I think that's the way to do it. So actually, we can do this with, really it would be like 2 passes. I guess it would be 3 iterations, really. I have an idea. Alright, ready? How much time we have? It took us a while to think that through. 20 minutes, okay. Not too bad. Alright, let's try this. Let's get our digits first. So... Alright. Going to say... How did I do this before? Digits dot pushback and modulo 10. We can say we use k. We need to keep n intact. Or we do. Maybe this is better. So k is greater than or equal to 10. Oh, actually. Yeah, it's a tricky thing. If k is greater than or equal to 10, we're going to keep taking the least significant digit. And then once we get to once we get down to 10, so we can have 0 through 9, the digits, then we push that back. So if we have 0, then we will still get a digit for 0. So this will always give us what we want. Now we want to, so say retrieve digits. Now we want to say is least significant. searching for any pair such that the smaller Alright, so we'll say in largest, start off at 0, or start off at 0. Well, really, I guess it would be -1. Then we're going to say for const and d in digits. I'm going to say if largest is not equal to -1. And then we say largest so if it's not equal to -1, then we're going to say if and d is larger than largest. Now we're going to say it's actually if d is smaller than, yeah. It's actually smaller than the largest. Then found a pair. I did this wrong. Okay, excuse me. I'm gonna use raw loops to do this. Okay. Excuse me. No. There could be more than one digit. So here's the question. We want the smallest digit to replace our new digit. Or, our index. So we want the smallest, larger digit. Interesting. So we just loop right up to this. Digit smallest. Let's retrieve a digit. Retrieve a digit to the right of the which index. Smaller. Yeah. That is smaller than the value which index. size of the smallest such digit. That's kind of a subtle point, but yeah, we want to do that, so we'll say in target index says -1, target values -1, and we'll say which value is digits of which. Alright, so now what we're going to do is say is less than which. If target value, if say if D is larger than which val, then we're going to set target index if, and then we're going to say, yeah, if that's the case, and say if target val is not equal to -1, now we're going to update target value equal to D and target index equal to I. Otherwise, say if D is less than target value, then we do this. Yeah, so larger than this which value, but the smallest of such values. Swap the I guess the resulting value index computation. Sort in ascending order remaining digits. Okay, so standard swap digits of which with digits of target index, which is guaranteed. There's guaranteed to be a target index of some kind. So we find the target index, we swap that, take the smallest number, that's still larger than this value. Swap that, and then now we sort the rest of the digits. It's actually going to be it's going to be a few things. So these are the least significant digits, so I can kind of look at sort of from, we're actually going right to left, but we want up to the so we just swap this which and some other index, swap those, everything to the right of this which value we want that sorted with the largest value to the right. So everything's reversed. We want this in descending order. Hopefully this makes some sense. So we want to use greater rather than in descending order. We want to do this. We can also sort and reverse, but we're not going to do that. We're going to use sort with greater than. And now we're going to build the desired integer. reds now. Yeah, that's fine. So the most significant digit will come first. Red is less than or equal to int max, or it would be limits, I think. It's, oh, that's not what I meant to do. How did I do that? Oh no. Uh-oh. What did I just do? Uh-oh. I don't know what I just did. I don't know what I just did. Anyway. Anyway, I think it's okay. I think it's okay. Wow. Wow. Okay, anyway. So anyway. Standard, I think it's numeric limits of int max. If we're less than or equal to that, then we can return ret as integer. If we're larger than that, then we return -1. Something like this. I don't know if it's numeric limits or something else. Oh, it worked. Wow. Not only did it compile, but it looks like it's correct in some cases. Alright, we're going to try some random digits here. See if any of those are correct. Yeah, so I got it right the first time, numeric limits. I think we're correct. I think we got it. Let's try some really tricky ones here. Alright. Let's go for it. How are we doing on time? 34 minutes, okay. Alright, I think we got it. There's gotta be some case here that's, yeah, I think that's it. I don't know. I guess we go for it. Maybe there's something I missed. Oh, we got it. Sweet. 100%. Easy peasy. Not bad. Alright, that's kind of it. I mean, there's not much to it. Yeah, this is relatively efficient because it's one pass to process the digits, another pass to find a pair. So two passes, third pass to find the other part of the pair, and then the fourth pass is to sort the digits. Excuse me, and then the fifth pass is to build the final digit that we're going to use. And that's it. Alright, sweet. So that's pretty good. Well, not a lot to say about that other than that's an interesting question. Took me a while, but we got there. Yeah, so have a good rest of your night. Talk to you soon, I think. I'm thinking about just going to bed. I don't know. I'm tempted to do another one. I think I just want to go to sleep. I think I'm going to err on the side of sleep. So yeah, it's been interesting. Talk to you soon. Have a good rest of your day.